Right. So we are going to start our discussion on fixed axis rotation, which is different from pure rotation. So what is fixed axis rotation? We had a discussion on this as opposed to something called pure rotation. So what we found is that we are able to do problems in pure rotation. And let's stick to the difference by a classic example. We have this scale and it's pivoted here, fixed, and the z-axis is the axis of fixed pure rotation, and that's our convention. And the scale rotates about this pivot. Now, in the fixed axis rotation, the scale is thrown into the air like a baton or like a juggler with his baton, and maybe we'll think of the baton here. The baton is in different positions at different instants of time, but what you realize is that it's, first of all, it's not a particle and it's rotating, and this is not pure rotation. I hope that part is clear. There is no point in the object which is completely fixed like this point here, like this pivot point here. Okay, so that's the difference. I'm sure you can see the difference. And now we want to do this problem of fixed axis rotation clearly, not as easy as this one. This one, for instance, we derived a very beautiful formula. Tau is equal to I alpha, and we know that we are focusing on the z-axis. Okay, so tau z is equal to I alpha. We know what alpha is. So how does one make predictions about the fixed axis rotation? And this is the final topic in this part of the syllabus for 11th and 12th, and it's very important to go slow. In fact, one would say worth going excruciatingly slow. So while let's actually take our time and fix certain notations. So for example, this is going to be the x-axis, this is going to be the y-axis, the scale is going to be this baton is going to be rotating in the xy plane. It shall not come out of the xy plane, and the rotation is about z-axis. Okay, so the axis of rotation is always going to, you can see that the object is rotating. The axis of rotation is going to be always parallel to the z-axis. Okay, so how are we going to go about making predictions for such motion? Okay, so now that you know what the problem is, let's get to our first main idea, and that is something a little out of the blue. There is something called Sassel's theorem, and we shall not spend more than a minute on this because we're going to go and simply accept it, and it's intuitively very acceptable, and that's going to form our basis of predictions. Okay, so it goes like this. So you are an observer in a inertial frame. Let's say it's fixed, and this is the z-axis, and you're observing this fixed axis rotation. So there's this baton which is going around, and fine, at different instants of time. Now Sassel's theorem essentially says that this motion, which is can be thought of as a combination of translation plus pure rotation. Okay, so I think this topic is also called translation plus pure rotation motion, and what we see now is that such a description is facilitated by Sassel's theorem. Now there is a discussion of, in fact there is also proof of Sassel theorem. It's on page 274 on the first edition of Kleppner and Kolenkov. Page 274, first edition, and of Kleppner and Kolenkov, which I keep calling as K and K. Right. But I don't think the proof is important. Now, what Sassel's theorem says is that if this observer has to give us a description of this object in different positions, he should tell us how the center of mass is moving in space. Okay, so the center of mass probably is going through a trajectory like this. So you should tell me what the coordinates of the center of mass is. That's the first thing. So maybe you can tell me what is xcm and ycm. Next, imagine yourself, let's take an axis, a dynamic axis that is always parallel to the axis that has been chosen, x, y, and z here. And let's assume that you're an observer who is traveling along with the origin, along with the center of mass. So the center of mass is turning out to be very important. Center of mass, okay. So let's say that you're traveling along with the center of mass and you're using this axis, dynamic axis. What do you see through your eyes for this baton? And a little bit of imagination will tell you what Sassel's theorem claims. You will see only, this observer sees only pure rotation. Okay, as you studied in the previous chapter. So what you will see in this is that, let's say that it has rotated now by some. So for example, if this is the x-axis and this is the y-axis, and this is the orientation of this baton, this is the orientation of the baton. Maybe I'll just choose a different color. So this is the orientation of the baton, this is the orientation of the baton, this is the orientation of the baton. So maybe you will see different angles for this orientation of the baton. So theta 1, and then this is a different theta, theta 2, and so on. So by describing to me xcm and ycm plus this orientation theta as a function of time, and obviously xcm as a function of time, ycm, any motion can be described by giving me these three values. Any motion of the kind that we are interested in. Mind you, I'm talking about the simplified problem where the baton is moving in the xy plane and rotating about the z-axis, the so-called fixed axis rotation. A simple example of this great topic called translation plus pure rotation. So what we need to do is accept Sassel's theorem and say that any such motion can be described by giving you these three values, that is the x and y coordinate of the center of mass, plus theta, which is the angle made through the eyes of the observer who is traveling with the center of mass. So now our entire focus will be on trying to tell you these three values, the different values of time. So let me write it down. Our aim is to predict xcm as a function of time, ycm as a function of time, theta t as a function of time, given xcm at time 0. How shall we write it? Okay, I hope you're okay with this. Ycm at time 0 and theta at time 0. So this is the claim that we'll be able to predict this at the end of the chapter. So, and this solves the problem, because Sassel's theorem says that you can solves the problem, because Sassel's theorem says that you can tell me the position, any translation plus rotation problem can be solved by giving these three values. Done. Now let's get to, so now that we've defined the problem, let's try to find out how are we going to go ahead with this problem. Our main beacon of light, our lighthouse, which shows the way to the answer, is the single law which says that torque is equal to dl by dt. Now this is what we need to depend on to find the answer, right? So before we get on to figuring our way out to use this law to solve the problem, let's have a look at this law again. It looks like I said, by the way, we have a clear idea of how to calculate torque. We have a clear idea of how to calculate L, and we'll see that if we manage to calculate both and put the equality sign in between, it'll actually give us the answers we are looking for. In other words, just the use of the law is going to take us home. But before that, just be a little bit more careful in the way we write this. This is important. Okay, now it's time to just go through this whole story one more time. We've had two laws which have helped us a lot, and both of them are vectors in nature, and it's worth writing down how they look so similar to each other and how we've exploited it. So here we go again. Tau system, torque is equal to dl by dt, and system. So what you need to do here is, first of all, realize the vector nature of this equation, and though we are well versed in it, maybe just write it down once here. This is actually not one equation but two equations, or if you're in 2D, on three equations if you are in 3D. So for example, you can write it as the x component is equal to the dp system x component by dt. Now please note that we are now in a scalar equation, and like that you can write a similar scalar equation for y. Maybe I should not be lazy. Is equal to dpy by dt system. So this is good, and we can write a third equation if you're in 3D. So pretty much something similar can be written down here, but like I said, we are going to focus on the one scalar equation which goes like this. So let's not forget this, because the general 3D problem gets difficult. So let's focus on this simple equation, and these are the situations that will be there in the syllabus, and believe me, this will be challenging enough. So in this particular section, remember that we are going to use only one equation, one scalar equation. Now the standard thing is, what if this is 0? What if this is 0? I mean, you know that px system is equal to constant, and this is called the conservation of linear momentum, and it could be that this is constant or this is constant, depends on it depends on whether the force is 0, right? And pretty much something similar happens if this tau happens to be 0. You can get, and this by now you will accept that it's a very powerful equation. Lz of the system mind you, is constant. So this is going to be called the conservation of angular momentum, and this is going to be called the conservation of linear momentum. Extremely powerful equations, right? Now what if this is not 0? Then there is a concept of impulse, and we call it linear impulse. And here, if this is not 0, we are still, the equation is still useful. We have something called rotational impulse, and so you can see a very parallel story in both of these. Now I would like to tell you that we're going to exploit this equation, all right, dl by dt system. Okay, but while we are exploiting this equation, I just want to highlight one thing. There are two different trends here. One, for a system of particles which can be anything, there is no limitation to the system of particles. You can choose any system of particles that suits you. At the same time, there is a parallel story running for a rigid body. Please be aware of this. The rigid body is a special collection of particles and like a scale and other things. But please note that in trying to understand this equation, we are going to follow both the ideas. So there are problems which will make you comfortable with a system of particles. There are problems which will make you comfortable with dealing with a rigid body. And right now I'm going to focus on this, and then we'll use this when we're doing problems. Right? So let me in the next video tell you how I'm going to exploit this for the rigid body, and then we'll solve a series of problems on the rigid body and also on exploiting the same formula for a system of particles. I think our main application is going to be collisions. Maybe I'll give you a graphic example of this. There is a scale, and then some particle m hits this, and there's a collision. Mind you, this is a particle, but the scale is not a particle. And then after the collision, maybe you can expect the scale to go tumbling down but also rotating, and you will be able to talk about such problems. This is simply the scale. Okay, what are the examples of this? Classic examples, we already seen dumbbell going in the air, but another classic example is you have an inclined plane. Let's say it's stationary, and then you have a solid drum or sphere or disc or hollow tire, and it goes rolling down this inclined plane, and while it's rolling, it's sort of rotating. At the same time, it's moving forward. A classic example of translation plus rotation. So these are the examples we'll focus on, but let us get back to the rigid body in the next video.